Hello, my name is Zi Zhang, and I'm from the University of New South Wales. I'm going to present the work PThammer Cross-User-Kernel-Boundary Rowhammer through implicit accesses. Here is the outline of my presentation. Firstly, I will briefly introduce the Rowhammer vulnerability. Secondly, I will talk about the limitation of existing Rowhammer attacks. Thirdly, I will introduce a new Rowhammer attack, the PThammer. At last, I make a conclusion of this presentation. So what is Rowhammer? Literally speaking, Rowhammer is to frequently access DRAM rows and induce bit flips in their adjacent rows. As DRAM rows reside in the DRAM bag, we firstly dive into the bag structure. So a bag has rows of cells, and each cell has a capacitor and an access transistor. The capacitor is in a state of either charged or discharged to represent bit 0 or bit 1. But these capacitors of cells can lose charge over time, so that we must periodically refresh these cells to maintain their charge. Typically, the refresh rate in DRAM 3 and DRAM 4 is 64 milliseconds. The density of the DRAM cells increases significantly. The DRAM rows can electrically interact with each other. In 2014, Kim observed that frequently opening rows N+1 and N-1 will cause some cells in row N leak charge at a much faster rate, such that these cells in row N cannot maintain their charge even when the DRAM refresh comes. We call rows N+1 and N-1 the hammer rows, and the row N is called the victim row. Besides, the memory access can cause the row open operations, indicating that the Rowhammer is a software-induced hardware vulnerability. To induce the bit flips, Rowhammer has three requirements. Firstly, the attacker has to avoid the cache hit, such that the DRAM accesses have to go through the DRAM memory, and this can be achieved by invoking the self-flush instruction. Secondly, the attack has to avoid the row buffer hit, and the memory access have to go to the DRAM rows directly, and this can be achieved by accessing rows N+1 and N-1 in turn to clear the row buffer. At last, the attacker has to perform frequent row accesses to rows N+1 and N-1 before the DRAM refresh comes. By doing so, the attacker can induce permanent charge leakage in row N. Up to now, the Rowhammer attacks have enabled privilege escalation, information leakage, etc., posing a serious challenge to the system security. For us, we have observed a limitation of all existing Rowhammer attacks. That is, the Rowhammer attacks require access permission to at least part of the exploitable hammer rows. We call these Rowhammer attacks as Implicit Hammer. As this figure shows, the attacker P in Implicit Hammer attacks will require access permission to these two exploitable hammer rows. So what is an exploitable hammer row? It is a row that is adjacent to a victim row containing sensitive data. Take this figure as an example. Rows N+1 and N-1 are exploitable if row N has sensitive data such as placebos. Also, for the Implicit Hammer attacks, either row N+1 or N-1 must be accessible to the attacker. So this limitation of Implicit Hammer attacks underlines the design of the state-of-the-art software-only defenses. These Rowhammer defenses are to make the exploitable hammer rows beyond the attacker's access permission, thus defending against the Rowhammer attacks. So our question is that whether Rowhammer attacks are feasible without access permission to exploitable hammer rows, thus bypassing the software-only defenses. We provide a positive answer to this question. That is, we are still able to corrupt row N when rows N+1 and N-1 are now inaccessible to the attacker. We introduce a new concept of implicit hammer. implicit hammer can void the access permission requirement. As this figure shows, the attacker T in implicit hammer does not have access permission to these two exploitable hammer rows. Instead, the attacker triggers a belong entity X to implicitly hammer these two rows. So the belong entity X could be either hardware such as a processor or the software such as the kernel. The tricks could be leveraging built-in features of modern hardware or software such as speculative execution, address translation, system call handler, etc. To demonstrate the viability of implicit hammer, we propose the PThammer attack, the first instance of implicit hammer. We have a key observation that pastable work could be used for implicit hammer. So the memory access triggers the address translation mechanism, while the address translation triggers the pastable work, which results in pastable access in memory. So here is a figure of the address translation mechanism. A virtual address will be translated to a physical address. So when we access a virtual address translation mechanism will be triggered. The processor will search TLB first. If there is a TLB miss, the processor will search paging structure for partial address mappings. And then the processor will search cache for all levels of pastable entries. If some of the pastable entries do not exist in cache, the processor will search them in memory. Intuitively, accessing pastables in memory is to hammer them once. So our challenge is to exploit the pastable work to produce frequent enough memory accesses to pastables. If we want to implicitly hammer all levels of pastable entries, we have to inject all the corresponding entries in TLB, paging structure, and cache. These injections might be too consuming, so a live implementation of pastable-based implicit hammer may be too slow to induce any bit flip. To address this problem, PThammer has identified the shortest path for hammering level 1 PTE. As this red solid arrow shows, PThammer can access the level 1 PT only. So if there is a TLB miss, the processor will perform the pastable work. If we keep the PD paging structure effective while cause cache miss for level 1 PTE, then we can access the level 1 PT implicitly. So if we can implicitly hammer level 1 PTE, if we can generate frequent enough accesses to level 1 PT in memory. So in this path, we have to induce two misses. The first is a TLB miss. The second is a cache miss for level 1 PTE. So our goal of this work is to generate frequent accesses to level 1 PTEs in DRAM memory. As an unprivileged attack process, we have low privilege to flush TLB and level 1 PT in cache. So we have to inject TLB entries and the level 1 PT from LLC. LLC is the last level cache, and it is inclusive of level 1 and level 2 caches. When we inject level 1 PT from LLC, the level 1 PT will be injected from level 1 and level 2 caches as well. So to inject TLB, we know that the TLB entry is indexed by virtual address, and the mapping between virtual address and the TLB has been reverse engineered, so that we can use this mapping to build a TLB injection set for a target address. When we access the TLB injection set, the address mapping for this targeted address will be injected from TLB. Also, we need to minimize the injection set size by TLB miss-induced access latency. So we remove one address from the injection set and measure the TLB miss-induced access latency. If the latency does not change, then we are sure that the removed address is not necessary in the eviction set. Okay, so to evict level 1 PT from LLC, we know that the LLC set is indexed by physical address, but we do not have the privilege to get the mapping between virtual address and the physical address. So we build a complete pool of eviction sets for each LLC set of each LLC slice. We also minimize the eviction set size by LLC miss-induced access latency, similar to the approach that is used by the TLB eviction. At runtime, we select the eviction set that will cause an LLC miss of a level 1 PTE for a target address. In this procedure, we firstly select eviction sets that have the same page offset as the level 1 PTE. We then access each selected eviction set and measure the access latency of the target address. The eviction set that causes the highest access latency is the one we are looking for, because this eviction set will cause the LLC miss of the level 1 PTE. So after addressing the problems of TLB and the cache evictions, we now can prepare the double-sided hammer. So we fill rows with level 1 PTs using memory spring. For example, rows n-1, n, and n+1 are filled with level 1 PTs. When rows n+1 and n-1 are implicitly hammered, then some of the level 1 PTs in row n will be B-flipped. So now we can perform the double-sided hammer. Firstly, we select a pair of addresses that their level 1 PTs are within one row apart, such as rows n+1 and n-1. Secondly, we build TLB eviction sets for the targeted pair of addresses. Thirdly, we select LLC eviction sets from the LLC pool for the targeted pair of addresses. From the 4th line to the 7th line, it is a loop. It is a loop for implicit hammer. In the 5th line, we access the target pair of addresses to implicitly hammer two level 1 PTs. In the 6th line, we access the eviction sets to evict TLB entries and the level 1 PTs from LLC. So after performing the double-sided hammer, we need to verify whether previous escalation has been achieved. If not, we need to perform another round of double-sided hammer. So originally, the victim row and the hammer row are filled with level 1 PTs, and all these level 1 PTs point to the user-created pages. So if there's a bit flip that occurs in level 1 PT of the victim row, and the flipped level 1 PT points to another level 1 PT in the hammer row, then a user virtual page is mapped to a level 1 pastable page, indicating that the user has gained the right access to the level 1 pastable page, and thus the kernel privilege has been achieved. So here is the conclusion. We have 3 takeaways. Firstly, PThammer, the first implicit Rowhammer attack, voids the limitation that underlies all the published Rowhammer attacks. Secondly, PThammer exploits the pastable work to implicitly hammer level 1 pastable entries and gain privilege escalation. Last, PThammer bypasses multiple advanced software-only defenses. That's all for my presentation. If you have any questions, please contact me through this email. Thanks a lot.